So, Manila has an international airport, and then they have a domestic airport, but they're not connected. So you get into the international airport, you clear customs, you clear immigration, you clear customs, you get on a bus. The bus takes you to the domestic airport. Then you have to go through, recheck bags, go through security at the domestic airport in Manila to then fly anywhere else in the Philippines. So you cannot have a tight connection in Manila. You will never, ever make it because you have to attribute, it's not just, oh, I can run across the Concord. You have to attribute getting on a bus and having the bus deliver you to the other airport. But like, you don't have to, like, for example, you know, a lot of times if you're cleared in the international terminal, you can then just go walk over to a domestic terminal and you don't have to go through the system again. But you do in Manila. You have to start all over again. Like you just showed up. Your Uber arrived in Manila and now you have to go through the entire process to go from Manila to Dumaguete. You don't have to go through immigration controls. But I was worried about getting back in with the government shutdown. I was worried we'd get stuck in, because we flew back through San Francisco. Literally, I've never cleared customs and immigration so quickly coming back into the US. In Miami, when we flew through Miami customs, it took us 6 hours to clear immigration and customs in Miami. It took us maybe 20 minutes. We walked through.
Yeah,
I mean,
it was so tough.
well, part of it is because it was the middle of the night, but I don't know. I mean, they had tons of agents, they had tons of lines open. We also didn't get secondary, they waved us through. So we didn't end up with a secondary inspection for customs. They just were like, yeah, whatever, just go away. So what was annoying was if you fly into San Francisco in the middle of the night, which we did, you're not allowed to check your bags. So we actually got in and we were through with everything at 8 o'clock, and there was an 8:45 flight, San Francisco to Phoenix, but my husband didn't book it because he's worried there was no way we could clear customs in time to make that flight. So the flight he booked was 6 a.m. the next morning. Well, then we could not recheck. We had to recheck bags and everything, and they wouldn't let us do it at 8:45. American would not take the bags until after midnight, but they're closed from midnight till 3 a.m. So we hung out in the airport for like 10 hours before it was time then to get on the plane to fly San Francisco to Phoenix. But no delays, nothing, no cancellations, no delays. Not even any really long lines. But, you know, you always allow extra time. So you always assume there's going to be a problem. All right. But no, it was a beautiful trip. They have gorgeous diving there. Visibility after the typhoon was bad. So we lost a day and a half of diving because of the typhoon, which is nothing to complain about because like 200 people died in it. So losing a day and a half of diving is not a reasonable complaint. And then they've got another one that hit. We flew out just in time because they had another one that then hit, and it hit right near Manila, just north of Manila. They had a second one come through. It's heading towards Vietnam now. But our plane had to change its flight path, so we technically were going to be we were technically supposed to land an hour later than we did, because the flight time changed because they changed the flight path to avoid the typhoon. So we went north and then turned instead of just going straight over. Anyway.
Do you know any mechanical engineering professors at the U of A?
Do I what?
You know any mechanical engineering professors at the U of A?
I know them. I don't know them as instructors. Like how well they instruct in a classroom.
Do you know Wayne Hacker?
Yes.
Yeah.
Now he should be good.
He's funny.
Yeah, he should be good.
I went to a class for fun to kind of see how like it is at the U of A.
Yeah.
And he's here. It's like a little cornball.
He actually taught at Pima. We trained him how to teach. That's the difference. And you can tell him I said that.
What do you think about the class? Like, they good?
He teaches the, his degree is actually, I think it's in math,
Yeah, he does fluids there. Yeah,
but he teaches applied math to engineers.
and it's nice because a lot of his like exams, he'll make part of it take home. So
You
he'll make,
know,
like 25.
that's actually not nice. That should make you
One of the
nervous.
professors I got.
nervous.
Yeah, because if you have a take-home exam, have you seen one of mine?
Well, I was looking at this one guy's and like 25% of the exam is take home. Like 50's in person and like the 25 they go over or something. I can't remember the exact criteria, but he'll like curve it. If people did bad on a part, he'll make the take home exam worth more credit.
Okay.
Yeah,
But you should,
be scared of take home exams.
you should be, because when you do it, this is the difference between take-home and in-person exams. Yeah, we have 2 minutes. In my opinion, well, not in my opinion, flat out, is the difference, is if you have a take-home exam, you have unlimited time and unlimited resources. If you have an in-person exam, in theory, and sometimes I get carried away, it should be written that you can take it in an hour and 15 minutes with limited resources. So that's the difference. And then the other thing that we worry about is you also now have the internet, which makes it even worse. Because, and so, for example, if you look at, if you talk to the folks, you talk to Kate or Tyler, because they've seen a take-home exam from me for fluids. So they had to do the problem in fluids. And then they had to do, and then I would say to them, now do this using a fluid of your choice. Or using, and I would give them really like, okay, now we're gonna do this problem, but we're gonna use concrete as a fluid. So they really had to go out and dig for information to be able to do the
Yeah.
problem. And, but I like that in that respect, because that's what you're gonna do in the real world. You're gonna dig for information.
And it opens up a lot of room for cheating because he was showing me like because you could see like the other people, like the average of the exams.
Yeah,
The take home was like 89%.
Yeah.
Like everyone did good. And then like the in-person part, it was like 40% to 50%. So like, and then he just makes the take home worth more credit.
yeah,
Yeah.
yeah, that works. I used to do that when I taught, like, well, you tutor. So when I taught like 151, I would have a calculator and a non-calculator section.
Okay, that's college algebra, right?
That's college algebra.
151.
Yeah.
That's the class I tutor, I think, most, and 142.
Yeah, well, that's because, I don't know, they're doing strange things. But everyone has to have college algebra. 142 is college algebra for liberal arts majors.
Yeah, a lot of people take that class.
Yeah, yeah, so it's, and if it's taught correctly, well, I shouldn't say that, but I guess it depends on who teaches it. It should be a very practical class for the students. So,
It's a lot of probability and statistics in that class.
and I think it's too heavy on probability and statistics. I would like to see them do a lot more spreadsheet work in that class. In fact, when I teach probability and statistics, I teach it with spreadsheets. So, because I think that's the only way. Why would we have students do it any other way?
Yeah.
So if we're doing statistics and probability, they should learn how to do it on a spreadsheet, especially if they're not a math major. I'm gonna take attendance. But that's my opinion, and that was the way I used to teach it. The same thing, I think, and I think it should be a lot more heavy on personal finance.
Yeah.
And in fact, I think everyone should have to take it from a personal finance standpoint. But the probability and statistics part, I would redo. I think that's a little math heavy, but they didn't ask my opinion.
Yeah, cause a tutor at my campus used to be a professor. He was one of the ones that made that class at Pima downtown.
Uh-huh,
And he says they butchered it with that, all those probability and statistics stuff. Like, it used to be so much better.
yeah. Diego, are you here? Yes, you're here. Logan, Logan's AWOL today. Riley,
No, Logan's
I'm
not
online.
I saw Riley. Is Logan here?
here. No, I think so. He hasn't been here all day, I don't think. He might be doing his DPQ exam.
Hector. Daniel. Gael. Gael's here. I just saw him join. Christian, I'm sorry. Chelsea. Ben, you're here. Valerie, you're here. Thomas. Demetrius, welcome to class. Anthony, welcome back. Alicia and Easton. All right, Max. Max was online earlier today. Max, are you here? Oh, Christian just joined. Atreyu. Julian. Oh, Julian's here. Julian, say hello in the chat. Jeremy. All right. Gabriel. There's Easton. Chase. Martine. Emiliano. All right, Luke. Michael. And Lorenzo.
Here.
Gael, I already marked you as here. You're in the other section. I have to go back there anyway, but I can double check. Oh, Chelsea arrived. All right. So let's see. We're still missing Logan. Gael already got you. Christian, you arrived. Chelsea arrived. And Easton arrived. All right. Okay, so let's go ahead then. And can you, those of you that are, oh, Max is now here. Okay. Oh, and Jeremy is now here. Yeah, Julian, I got you. All right. So Zoomers, can you see my screen about heating exchangers and throttling devices? Okay. If you arrived late, I already took attendance. I'll take it again at the end. I didn't think about it, but I had some international students in. Or they're not, at least in Arizona, some students in dynamics. Because Arizona does not do daylight savings time, so. All right. So you're gonna have to tell me. I thought we did a heat exchanger problem, is that correct?
Yeah, we did like one. Maybe like that one.
Okay, did we do this one with the steam? Okay, I'm getting some no's in the classroom. All right, so let's go ahead and let's see. Got a table note, so do I have the table in here? So you guys go ahead and get the problem down and I will pull the table for this problem. Let's do a freeze on that. Okay, I stopped sharing for just a moment. I will be back. I'm just pulling up this, I need to pull up this steam table and it was freaking out. Zoom gets upset if I move away from the Zoom screen. Hector, I took attendance. I'll take attendance again at the end of class. In case we have any folks who are not in Arizona and assume there was daylight savings.
So M dot is the mass flow rate.
Correct.
Is there what about volumetric flow rate?
V dot.
E dot, okay. And Q dot is when you have kilowatts. And as opposed to
Q dot.
joules or kilojoules? Would that be Q dot when you have the heat transfer? Rate of
Yes.
heat transfer, okay.
Okay, give me a 6 when we're ready to go on this problem. Got some folks still writing it down in the classroom. Hopefully you guys had a good week last week. No? Got some yeses, got some nos from the classroom.
when we write Q on like our diagram, if we don't know if it's negative or positive, we draw like two arrows, one on each side or something. Cause if heat's leaving the system, Q is negative. If heat's going into the system, Q is positive.
Correct.
Okay. Does that matter for this scenario? No.
For this scenario?
Yeah.
Yeah, well, heat's gonna be leaving the system for this scenario, but yeah. All right, I'm looking for a 5 or a 6 in the chat. Can you guys hear me? Once you've got this problem. Anyone there? Oh, you just log in and then go make coffee. Oh, okay, so you can hear me? You guys are getting the problem down. In class, folks have the problem down. Demetrius has already finished working it. No, he says no. Not buying it. All right. So this is going to be a heat exchanger problem. If you would like the reference in the book, we just had it. This is 4.61. The other problem I don't have a book reference for, so I'm not sure if it came out of our book. But this one is 4.61. All right, so steam with a quality of 0.7. The minute I see the word quality, what does that tell me? Okay, that's going to give me my X. Which region am I in? We're in that center part, aren't we? We're in that mixture region. Has a pressure of 1.5 bar and a flow rate. The word flow rate, okay, pressure is P, but the word flow rate, what does that mean? What are we looking at then? We are looking at M dot. Enters a steam separator operating at steady state. Saturated vapor, now, do we still have a quality? No, because it's saturated vapor. It's 100% vapor. 1.5 bar exits the separator at state 2 at a rate of 6.9. So this is another M dot. Saturated liquid, meaning we're all liquid, correct? Exits the separator at state 3. All right. Neglect kinetic and potential energy. Determine the rate of heat transfer. So we're going to want to determine Q dot. All right. And its associated direction. So is it giving heat off or is it absorbing heat? All right. So what's happening here? Let's go and draw a picture. I'm going to draw it like this because I've got steam leaving and I have liquid leaving. All right, and then I have a mixture entering. So here at our entrance, what do we know? Well, we know X equals 0.7. We know we have a pressure of 1.5 and, oopsie, that didn't even look like a 5.
Would there be two exits?
Yes.
Okay.
Okay, so a pressure of 1.5 bar and a flow rate of 10. That's in kilograms per second. So that's what's coming into it. All right, now what it's doing is it is separating it. So when it's separating it, we have the vapor coming out. So this would be my vapor then. Okay, so a mixture is pouring in, vapor is coming out, and we know that that pressure is 1.5. We'll call this 1, this 2, and this 3, based on what the book, how the book has things, or what the description has it labeled. All right, and then, and we know, what else do we know? We know this is M dot is 6.9. All right. Okay.
When it says state 2 and state 3, that just means like the exit 2 and exit 3? or-
Yes. All right, then what's coming out of here? This is strictly liquid. And we're told that it also has a pressure. So we'll label this pressure 3 is 1.5 bar. We'll call this pressure 2. And we'll call this pressure 1, just so we can keep them straight. All right, so we're also told that we are operating at steady state. So what does that mean?
E0.
Right, this is gonna be 0. And we're gonna neglect kinetic and potential energy effects. So let's go ahead and write out our equation. So E dot is then going to be my heat, which is what I'm solving for, minus my work. And then I'm gonna write what I have here because the author plays games with these signs, it drives me crazy. Oh, that needs to go on the inside. All right, let's talk about this and we can then move forward. All right, so we already said we're at steady state. So this is gonna go to 0. Is there any work being done on this system? A resistor, a paddle? No. So this is gonna go to 0. We were also told there were some things we can neglect. What can we neglect?
Kinetic and potential.
So both of these are gonna go to 0, correct? All right, so let's see what we have left. We have left Q dot CV. That's what we ultimately want to solve for. By the way, what does CV stand for? What?
Control volume?
Controlled volume. What did I hear? Ben, what did you say? Anthony, what did Anthony say?
Didn't say anything.
Constant volume?
Constant volume, okay. I thought I heard impossible.
I said constant too, but I thought it was wrong. Just.
All right.
Damn, yeah.
If I turn my hearing aids up any louder, I'm just gonna put them on a different setting. All right, so. Okay, so let's go ahead then and talk about what's going in and what's going out. So coming in, when we now deal with this scenario here, right, what do we have? We're going to have the rate at M1, and then we're gonna have the H at 1, correct? And that's what's coming in. We're gonna subtract what's going out. So we're then gonna have the mass rate at 2, right? And then we're gonna have to deal with our mass rate at 3. Some of these are gonna be easier to go after than others. Hey, I took attendance, so check in with me at the end of class. All right. And I know you guys all got attendance notices, and it's because it's such an amazing system that no one else could get into the attendance but me. So my boss can't get in. I couldn't give anyone else permission. My subs couldn't get in. It's just the way it is. So you got an automatic email response. No, you've not been dropped from the class. It's strictly I was not in country to take attendance. Yes.
I had a question too about the queue.
Mhm.
So it's labeled as like, or we can assume that's leaving the system, like heat is being taken from the system. Would you label it a negative right now, or would you wait till it's on the other side?
Yeah, I'd wait till I solved it.
Okay.
I'd wait till I solved it. All right, so, I mean, we know it's gotta be leaving the system.
Yeah.
Right? But, so it should be negative then, correct?
Yeah.
but no, I'd solve it first.
If you just keep your signs consistent throughout the problem on it. we're gonna
Yeah,
solve it.
then they'll work out at the end. Okay, what else do we know? We know that that's a potential issue. I skipped a bunch of steps on this. That was very nice of me to do that. All right, what else do we know? Well, we know conservation of mass, don't we? So that means M1 has to equal M2 plus M3, correct? H's, we're gonna get off the table. All right, so let's figure out what then our M3 is gonna be, because that was not given. So M1 is given to us as 10. So this is gonna be 10, and this is in kilograms per second, is then going to equal, I lost it, 6.9. 6.9 kilograms per second plus M.3. There is a dot there. I was told that doesn't always show up virtually. All right, so if we subtract them, then M3 is going to then be 3.1 kilograms per second, correct?
Yep.
All right. So let's go ahead. Now we have M3. We can go after the H's. Everything is happening at 1.5 bar, isn't it?
Yeah.
So if we look at our property at 1.5, right, our pressure here is 1.5. We have our volumes, but let's go over here because this is what we care about. Here are the H's, correct? The 461 is my fluid.
467.
467.1. Right? That's gonna be my fluid. Now, this is why I wanted for us to do this problem. This is, let's talk about what H is and what this means here. All right, so physically, H is enthalpy, which is what? How much heat it can absorb before it changes state. When we do this, because enthalpy is a little different, we're gonna wanna use this as our upper side for the in-between. So this is going to be H, which with 3, right? That's the stuff coming out the bottom.
Yeah.
This is gonna be then H2, that's the steam. All right, I'm gonna have to use these two numbers because H1 has to fall between those two numbers.
And that's because of our X, right?
That's because we're given X as quality. All right, so,
You have to multiply that by X or?
well, no, we put it into the equation that we use for X, right?
Yeah.
The equation that we use, we can use for all of them. So H1 is then gonna be H of the fluid 1 plus X, right? Except now we're gonna use H of the fluid and gas 1 instead of the subtraction. We'll actually end up with the same answer, but is that what?
It's just a way to solve the word that should like slightly.
Well, enthalpy is a little different. All right. So this is, so this is a slightly different way to solve it. All right. So the fluid was what, 4? Did anyone write the numbers down?
The mass.
467.11.
Oh,
467.11 plus my X was 0.7
yeah,
and the other one was 22.
226.5.
22.
26.
Yes,
Okay, try it again. 226.
2226.
3 2.
There's 3 2s, 0.5.
All right, excellent. All right, so plug in your calculator and what do we get for H1? Like 2025?
$2025.66.
All right. 2025. All right, so let's head back to our equation. We're then gonna have, we know our M1 is going to then be 10 times 2025.6. We're then going to need to subtract our M2. Now, our M2, we said was strictly vapor. So we can pull that off of our chart, can't we? So that's gonna be the 2693 number, correct?
Two.
All right, we're then gonna have our fluid number, which is the 467. So this is then gonna be 3.1 times 467.1. Nice and loud, what's wrong?
I'm confused where that 2693 came from.
It's our HG, right?
Did I write round wrong? Oh, it's 2693.
Oh, I didn't see that. Okay,
Oh, no, I'm okay.
yeah.
I'm okay. All right. So what happens when you plug this in? I'm gonna move this to the other side. Right, plug that all in, and what do you guys get?
Minus 40,291. Oh, the first one's a plus? Okay, I did that wrong.
Okay, because I'm like, that's kind of crazy. Yeah, the first one's a plus because it's going in. The other ones are minuses because they're leaving.
Oh,
Anyone get 227.7? Gabriel, is that what you got?
I got 222. I think I might have.
Oh, no, that could be it. It could be a rounding error on my part. Anyone else do it?
222.719.
Oh, okay. All right, now, this ended up being positive. We're gonna move that sign over. Ben was trying to figure out the sign before we did the problem, which you could as kind of a check. By the way, units on this are gonna be kilograms. Oh, it's gonna end up in kilowatts.
I just like drawing it on my diagrams. I know.
Oh, okay.
Well, you can make an assumption.
Or Q. -2.
All right, so, but you could also, since this is negative, right, then we know that this is, Q has gotta be leaving. Right. Questions on the problem?
Yeah, I do. Why in that form to find H1, why do you have to add the enthalpy of the fluid plus the gas mixture?
Okay, so if we, I should have printed this out because you guys make fun of me about this. Quality, right?
Yeah.
That's gonna be H1 minus
Oh,
H fluid, thank you,
okay.
H
Gas.
minus H fluid.
Mhm.
So that's why. The table gives us this,
It gives it as, that's what's in the parentheses.
right?
Okay. Okay, I get it.
Yes,
So on that note, so we said that HG and HF were H2 and H3, right?
yes,
Okay. Okay. I was just making sure. So whatever pressure it is,
well, but what we did, the thing about the pressure is if the pressure had changed, this problem would be a lot more exciting. But the pressure is constant throughout, right, Jeremy?
Right.
So because of that, we are literally only dealing with this particular table.
Right, okay. That makes sense. So yeah, so if it's pure liquid or pure vapor, you just
Right.
use those, but you need to find the enthalpy of the mixed region, basically.
Right. We don't know where we are in the mix.
Right,
That's why we had to use the equation to solve it using the quality.
that makes sense.
Right.
And that X works for everything on that table, right? Like if we needed like internal energy, we can use that X value too.
Well, what's awesome, yes, what's awesome about the quality is it works and hopefully we're gonna get into this today. Yeah, we will. All right, it worked, we found it worked with volumes, doesn't it? We also can use it for internal energy. We also can use it for enthalpy. We're also gonna be able to use it for entropy. So X works no matter what quality or no matter what I can't find the word. It'll pop into my brain. No matter what property we're looking at. Yes.
If we weren't given the mass flow rate for 2, could we have used the quality to figure out the amount of steam and just assume that would be the flow rate? Knowing that's gonna be about 70% steam.
Yeah.
Okay.
I wouldn't, I mean, I would be careful about doing that, but yeah, you could do it that way. You could think of it that way. It's gonna work out. All right. Okay, we doing okay? I'm getting a lot of apprehension. Is the apprehension over this problem or just in general? General, okay. It's just that time of the semester
Yeah.
where you guys need a break?
Yeah.
Not from me, but from school. You guys are gonna love the 8-week schedule. Oh, you'll all be graduated by then.
8-week schedule.
So,
Pima's gonna move to an 8-week schedule during the school year, during the fall and the spring. No. It'll be 8 weeks and then you'll get a week off.
Oh,
And then it'll be another 8 weeks. That's my understanding. I could be wrong.
Oh, there's still 16-week classes.
No,
No.
everything will transfer. Everything will become an 8-week class. But you won't take all these classes. Does that make sense? You take 2 the first 8 weeks and 2 the second 8 weeks.
They learn better when it's over a longer period of time.
Yeah.
Oh, instead of taking 4 at once.
Instead of taking 4 at once, you would take 2 the first 8 weeks and 2 the second 8 weeks.
imagine doing that electrical class in 8 weeks.
Oh.
But you wouldn't be doing
Be a
anything,
sprint.
you would, but see, then you would have to balance it. If you're doing that electrical class, right, maybe you take a gen ed with it.
Yeah.
Okay, you wouldn't have electrical and DiffyQ and statics
Yeah,
and dynamics, or not dynamics, but and thermo.
Yeah.
This is the worst semester for all engineers. Has anyone told you that?
no, but I'm
I
happy.
figured that out on my own.
Yeah.
Right.
Adventure.
Right, so when I went to school, this technically is first semester sophomore year, right? When I went to school, this is where everyone dropped. If you make it past this semester, you're gonna be fine. Okay, but this is the worst semester. It's called the horrible 4 for a reason. This is the worst semester for engineering students. Horrible 4. They're either Cal 3 or DiffyQ, doesn't matter. And then they are the electrical class, statics and thermo.
Statics is fun.
I'm glad you have a fun class this semester.
It's like my break class.
It's your break
It's
class?
my break class.
All right. Valerie walked into statics and goes, this class is easy because everything is 0.
Yeah.
Everything equals 0. Okay, so, but no, this is a tough semester for all students. All right? And I think we make it tougher than we should, but we have not had a brain shift in engineering yet. We shall see. If we ever have a brain shift in engineering. I don't know, because I think part of it is okay, so basically you're gonna use tables all the time. No, I meant that in a big picture. When you don't need to use tables is when you're dealing with ideal gas laws. Okay, ideal gas does not work with tables.
I guess my confusion is like, not the fact that if we're still gonna use tables, but when to use the values, and if we could use, like, if we pull a value from the table, like if we were able to use it for a different, I guess, equation. I don't know. I'm just still confused, like on how, like what values to pull, when to use them, and just knowing, like at first what values to pull.
Okay, all right, so,
Like I understand how to find them,
right,
but I'm not, I don't know when and where
so,
and if they like can be used other places.
okay, so this is where I think the biggest confusion for the tables come into play, right? And that is the fact is you need to know where you are. Here, you're at saturated liquid. Meaning it's all liquid, right? Here you have a mixture. Here you have saturated vapor. What I tell students, and this works most of the time, is start, if you don't know which table to use, start with the mixture table. Okay? If what you're looking at with what you're given falls outside that mixture table, then you're gonna go, then figure out, are you vapor or liquid, and then go use that table. Yes.
When you're saturated liquid or saturated vapor, you're on the line, right?
Well, yeah, when you're saturated vapor, you are, yes, you are on this line here.
So that's BG.
Right, that's your VG. Okay, unless, right, and this is why you have to look at it. Let's go back one, right? Let's say we're given volume and our saturated vapor at 1.5 is a 1.159 for water. Let's say it's at 3. Can I use this table? No. This table only works when the volume's between 1.05 and 1.159. All right. Or if you're given internal energy, these are the internal energy this table works for. Or if you're given enthalpy, that's the entropy that this table works for. This problem starts, Gael, by telling us we're given a quality. So that automatically means we're going to be on the A2 or A3 scheme tables. Okay, we're not on the A2 because we're given pressure instead of temperature. Yes, Valerie.
I think it's also important to figure out what equation you need to use to solve it, because if we know we needed the equation you wrote down, we know, oh, I need to look for enthalpy in the table.
Right, so unless we're dealing with ideal gas.
Yeah.
And things are gonna get a little different, hopefully today, maybe not. Entropy is gonna be different. We're looking at this equation.
Yeah, but earlier in the semester, I was using change in internal energy equals Q minus W. Because then you're looking for U in the table. So
Correct,
it depends on which formula you're using.
right, but what's the difference between those two equations?
No mass moving out of the system or in the system.
No what? Not no mass.
Mass, right?
Mass flow rate. If we have this equation, nothing is moving. So in the beginning of the semester, stuff didn't move. All right? If we're told mass is flowing, then we're going to have to use this equation.
Let's go back to our open, closed, and isolated systems.
Does this go back to it?
Yeah.
No. Open, close, and isolated systems won't have no flow rate. So yes, it does. All right, if it's closed or isolated, it's gonna have to use this, correct? Because mass is not moving in or out. If it's closed and isolated, then what else? Q is, if it's isolated, then Q, or isothermal or isolated, then Q is gonna be 0.
Yeah.
All right, so that's the difference between using these two equations. Does that help? All right, Gael, does that help?
Honestly, not really. I know
Okay.
I know what tables to look at, and I know when to use which formulas. I think what
Okay,
trips me up the most is like whether, um, like, I guess for example, like if we have the equation on the bottom, um, I don't really know how to explain it, but I remember in the exam also, like, I didn't know whether to go
please
all
do not
in.
discuss the exam. I have a couple of people who asked to take it late, and since I wasn't in town, so if there is a problem with the exam, Gael, we're gonna have to meet office hours for that at this point.
I wasn't gonna go into specifics of it, but if that's okay, like I'd like to talk about it generally, or
Yeah, yeah, we
um,
can talk about it in office hours.
okay, never mind then.
Okay. So the other equation, and I thought maybe this is where you were going with this. Is if you're given the specific heat. Right? If you're given the specific heat, you can find enthalpy this way. Which is kind of the more accurate way to do it.
Dr.
Right.
Minky, I remember
Yep.
when I was doing the homework, um, I like would get tripped up also like when either to go all in using the formulas or just keep pulling values out of the table because I feel like it just made sense or just to pull values from the table and just plug them into whatever formula. But also I felt like in some cases I could solve for the value I was missing. So I wasn't sure what to do basically. I think that's my biggest confusion. That's why I don't know what when to pull values, I guess, and what values to use and what not to use. Stuff like
Okay.
that. I don't know if that
Yeah, I think we're gonna have to sit down and look at some problems in particular in office hours if you want. Because I really kind of need to get to this today. Yes,
Should be CP, right? CV, is it the stage?
it could be either one.
I thought you use CV when it's internal energy, CP when it's.
Yeah.
Oh, okay. So CV is internal energy and CP is change in is enthalpy.
Yeah.
So check real quick. Yeah,
Yeah, that's
CV
right.
is U, CP is H.
I don't even know where I wrote it down.
It's right.
Okay, so it should be C sub P. Meaning we have a constant pressure, but we're looking at specific, if you're given specific heat, you can calculate out H and U. If you're not given that information, pull it from the table. All right, so, or if it's something that isn't on the table because it's not a fluid or a gas that we have information for, correct? All right, so let's talk about throttling devices. Throttling devices change what? What are they gonna change?
Velocity.
They're gonna change that flow rate, aren't they?
Yep.
Right? So they do not provide energy. What happens is, and I'm gonna use the word convert, which is not the best word to use. But we'll go with it. They're gonna convert pressure energy right into thermal energy. This is the biggest key. You know, this is the key words you're gonna look for when you do a problem to tell you it's a throttle device, right? Large, irreversible. Pressure drop. Right, the keyword there is irreversible. Got a problem and it's missing the keywords, but that's okay. It tells us it's a throttling device. All right, so I need to grab a table for the problem. We'll talk about why we grabbed a table for the problem based on what information we have. So go ahead and get this problem written down. I do not have it in my notes if this came out of the book or if I pulled it from somewhere else. Okay, so give me a 7 when you get this down. As I said, I need to grab a table. And I'm gonna grab the table for this. First off, it's ammonia. So Gael, let's walk through this. If it's ammonia, am I gonna use any of the steam tables? Yes or no?
Wait, no, not a steam table.
I'm not gonna use a steam table. I'm gonna have to look for a table that is what? All right, I'm gonna have to look for a table that's ammonia. Actually, you know what? Let's walk through this together. Let me know when you have this problem. Let me know when you have this problem down.
So is this kind of like a diffuser because the pressure's dropping?
No, because the pressure's dropping because there's something blocking it,
Okay, okay.
okay? On a diffuser, the pressure's dropping because you have a change in surface area.
Yeah.
Okay, are we good in class?
Yep.
All right, I need to, oh, well, I just turned something on. That was bad. Okay, I'm gonna unfreeze this. I need to share this. Yeah.
Just like based on what you're saying, isn't it kind of like well, I guess it'd be more like a nozzle, right? Because like you're having a change in area. That's
Correct. It's just a different, you still have a change in area. It's just physically a different, like if you're in the field and you have a nozzle or diffuser versus when you have a throttle valve, it's gonna behave, you're gonna look at it differently. You can look at them as being the same for this class. When you take fluid mechanics, they're going to be different.
Okay.
All right, so first thing, Gael, are you with us? This is for you.
Yes.
Okay, so first thing is I have ammonia. So I need to go to my ammonia table, correct? I'm given 2 pressures. We're going from 16 bar. All right, so we're going from 16 bar all the way down to 4 bar. And in addition, we're at 100 degrees C. So we're looking here, 16 is roughly this number. Would you agree for a pressure? And we're at 40 degrees. That's going to be a problem for me, isn't it? All right, if I go to the pressure one here, if I have a pressure of 4 degrees, this is negative 1.90. Do you see that? So if that's my temperature, if this is my pressure and that's my temperature, and I'm at 100 degrees C, can I use the mixture table? No. Am I going to be a liquid or I'm going to be a vapor at 100 degrees C? Okay, so superheated ammonia, right? If I have a pressure, now we're looking at this pressure, 2.5, 3. Here is my 4 bar, correct? So here is what happens at 100 degrees and 4 bar.
At 16 bar and 100 degrees.
Yeah, 4 bar is the exit. from-
Oh, 4 bar is the exit. Okay, so 16 bar. Here we go, 16 bar and 100 degrees. Right, we're coming in here, aren't we? All right, so I'm gonna pull this table and put it on the other slide. Okay, so did you understand the logic I used? And maybe that's part of the problem, is you do need to use logic to figure out where you're gonna be with these. All right, it's not just a formula you can use. So let's go back to here. Let's go to here. Go. Let's reshare with the Zoomers. All right, so coming in, we know we're at 4 bar and we are at 100 degrees C.
No,
16.
16.
Or I'm sorry, this is actually a stupid problem. Okay, that's fine. We're at 16 bar coming in. We're at 16 bar and we are here at 100. So what is my H going to be then?
1644.
All right, it's gonna be that 1644 number. Okay, so let's go back to our problem. All right, so let's talk about what's going on here. We have a throttling device. Right, and so we have stuff coming in, and then something's happening here, causing it to throttle, and then we have stuff exiting. Velocity in, velocity exiting. We have information about what's coming in. This is 16 bar. Temperature coming in is 100 degrees C. All right, what else do we know that's coming in? Well, off the table, we can then get this 1644.56. Okay. What I should have written on the previous slide, which I didn't, right, is when we have a throttle device, internal energy is constant, or, well, it's conserved. Sorry, enthalpy is conserved.
Why is that?
So it's because the pressure energy is being directly converted into thermal energy. So therefore, that's not going to, your enthalpy is not going to absorb any of that energy. All right, because what's going to happen is it's going to be released as heat. Yeah.
And so just to clarify, like a throttle device is literally just a device that has like an opening valve or like an adjustable
Yeah.
valve that can adjust the pressure and speed, right?
Right. So these are our throttle devices.
Is my thumb on a hose a throttle device?
Right. Right. When you put your finger over a hose, you're putting in a throttle device. Didn't you have to do that?
Yeah, for one of the pre-class quizzes.
Yeah. Okay, you creating a throttling device. When you step on the gas in your car, you're changing a throttling device, aren't you? Right? Because then the valve opens to let the gas out. Unless it's electric. And then it's just electric. All right. All right, so. So my H is conserved. Because of that, I know my pressure at the exit is the 4 bar. All right, I don't know the temperature at the exit. But the enthalpy at the exit has to be 1644.56. All right, now, that's why I said, I thought this was a much more, I actually did the analysis to figure out what the exact answer was. Because this isn't gonna be exact on our chart. So if that's, we know we're now at a pressure of 4 bar. If we go back, and I'm just gonna grab it. So I'm not switching slide, or I'm not, so hang on, Zoomers, I know you can't see what's happening. All I'm doing is I'm heading up to 4 bar.
We should keep enthalpy where it is, the internal energy's going up. The volume's going up. Because enthalpy is related to delta U plus PV, right?
Right,
So
that one
keep
could
going
change,
down.
yes,
Okay,
but the H does not change.
Okay.
Right,
because it has to balance that equation outside that the internal energy is going up or the volume's going up.
correct. All right, so if I go back, because I know exiting, I'm at 4 bar. All right, so if we're at 4 bar, right, and we're dealing. Oh, okay, I see what this is. Okay, and we've got this 16, it's gonna be between these two numbers, isn't it? It's gonna be between those two, correct? All right, I actually did the linear analysis in mind, but is it gonna be closer to 80 degrees or 100 degrees? 80 degrees. All right, and so that's, then our temperature here is, you're gonna be able to put down to 80 degrees. If you actually do the linear regression, it comes out to be 83 degrees C. All right. All right. So I have 15 minutes. We're gonna use them. All right, I do need to change slides here, because I need to pull up a different set. So let's go ahead and do that. We want 5.1. 232. Right. We're gonna move into talking now about entropy. And I believe I owe you some homework worksheets, correct? Because I wasn't thrilled with the stuff in the book. I didn't think it was challenging enough. All right, so. All right, so can you see, let me know in the chat, so every time I do that, I lose the chat. Let me know in the chat if, that's not help. That's participants. Chat, there we go. Let me know in the chat if you can see 5.1 through 5.3 second law of thermodynamics. All right, so let's get entropy defined. We won't get any problems worked today, but we can go ahead and at least get it, the definition done up. Okay. We are going to look at the second law of thermodynamics, and that is the law that governs entropy. Entropy is another character of our characteristics of our material. All right, the second law of thermodynamics is that entropy will always increase. Now, we got to be careful with that. That means entropy of an entire universe will always be increasing. Okay, the system might not, but entropy of the universe is always increasing. The symbol for entropy is an S. Okay, now what entropy is entropy is our disorder. Right? You can also think of it as chaos. All right? And so when we're dealing with entropy, that's what we're looking at. There is, from a modeling standpoint, all right, there is an entire field that does chaos modeling. It's actually really cool because they do develop patterns after a while. Chaos isn't really chaos because you will get patterns when you do chaos modeling. It's kind of interesting. But cool, and I'm thinking about it when I took chaos theory, and I don't think I have, and I wrote some computer programs, but I think that computer died a long time ago. All right, so let's do an example of this. If I have a bunch of gas particles, right, and I'm inside, and this is a vacuum. Sorry, I'm having a spelling delay. Vacuum, V-A-C.
A W, but not a double.
Okay, let's try it again. V-A-C.
U-U-M.
Okay, are you sure?
Yeah.
It's such a weird word. All right, if I say I'm gonna remove that barrier, what do you think those gas particles are gonna do? They're gonna spread out, aren't they? So when they spread out, we're gonna see an increase in disorder. So this is going to be an increase. Now, typically, we don't calculate S directly. We spend a lot of time looking at delta S, all right, which is then the change in disorder or the change in entropy. I said entropy only increases. If we are dealing with our closed system, then it might not change. Okay, so here is another picture of this, right? Done more professionally, that yes, was stolen off the internet. But I don't make any money doing this. Well, I don't make any money off of this image being on a slide. All right, so if we start with high randomness, right, and then what are we doing? You can think of it that we're compressing it or we're bringing the temperature down, right? What happens is that delta S is going to decrease. So we end up with low entropy or low disorder, low chaos, low randomness, all right? This actually also comes in to another law of thermodynamics, all right? And that law, S is zero when we're at zero temperature, we're at zero S. Okay, meaning there's no disorder. So when we're at absolute zero, there should be no disorder at all. All right, so let's review some vocab. And let's look at reversible versus an irreversible system. When I tell you it's a reversible system, what does that mean? You can do work to it, and it can go backwards, right? Put in work. If we have an irreversible system, and we actually just talked about this word. You know, you can't put the genie back in the bottle, right? That's an irreversible system. No way it can go backwards. Right, so if you start with a pot of water, put it in the freezer, what's the pot of water gonna do? Right, it's gonna freeze. If I pull the pot of water out and I set it on the countertop, what is it gonna do? It's gonna melt and it will have not changed, correct? Have the same amount, the volume will change because when it freezes, but you know, we'll have the same amount, a total amount of water molecules. Now, yes, Lorenzo's going, well, wait, on the surface, you always have some evaporation. Yes, Lorenzo, but it's minor. We're not gonna worry about it. Okay, then if we take our pot of water and I put it on the stove, what's gonna happen? It boils, steam, not gonna be able to put that steam back into the pot. All right, there is a way to do it with condenser coils, but we're not making moonshine.
Can we?
He said, damn it. Daniel would show up for that.
All right, so let's talk about what happens then when we have our how heat transfers and then how that's going to affect our entropy. By the way, let me go back to that previous slide because entropy is, we're going to use entropy to figure out if it is reversible or irreversible. Oh, that's if delta S equals 0. But that's coming off the top of my head, so be careful. Don't leave that statement alone for a moment. All right, let's talk about heat transfer. Right? If something is boiling hot, it's going to want to get colder, correct? All right, so what's going to happen is this is considered a spontaneous reaction. If I have a boiling pot of water and I turn the heat off, it's going to want to move back to room temperature. All right. And so it wants to go, this is going to be a lower entropy state. Lower energy state, lower entropy state. So if we have, by the way, if we look at the universe as a closed system, I think it's estimated it's like 10 raised to the 26th is when the universe will have entropy death. Okay, I don't plan to live that long, so we won't worry about that. Yes,
Like, do you know there's a formula for enthalpy? Is there a formula for,
entropy?
yeah?
Yeah, thank you. Okay. All right,
Next slide.
so the wonderful thing about entropy is, my husband is calling me, he can wait 4 minutes, is that the entropy is then equal to dq over t. Okay, so dq, this is what, or we could write it as q dot. This is our heat transfer. T is our temperature. All right, it's reversible, and I was right. When it's reversible, this is going to then equal 0. All right, So if it's positive or negative, if our DS ends up positive or negative, then it's not going to be, it's going to be zero. If it's reversible. So we're gonna use, we can use this to figure out reversible systems. Now, we have to be careful because it changes based on the type of system we are using. All right, if we have a liquid solid system. All right, then delta S is then going to be what I just wrote, dq over t, or we can then find x, s as dq over t. That is not usually the way we write things, all right? If everything in that equation goes to, everything in our closed system equation, if it all goes to zero, well, let's write it out, because we want to rewrite this in another way. E dot equals Q dot minus W dot plus M sub I, H sub I. If we are strictly looking at a heat transfer happening, all right, steady state heat transfer, steady state, that's going to be zero. If it's a heat transfer only, all of these terms are going to go to zero for me. All right, so that means my Q is directly then related to M dot H dot, or you could think my Q is then going to be my internal energy. What's up?
Oh, is it asking if you said if it's a heat transfer, that's when
It's
those things go to zero?
Right.
Liquid is solid.
Right, when we're in a liquid to solid
Okay.
or solid to liquid. Okay, so we already know what, we know something about this H here, don't we? But you said it was CV.
It's CP. That's right. It's
So,
CP.
H just deals with CP or CV?
CP. Internal energy CV.
Internal energy CV, right? Then this is then the change in temperature, right? So if we're saying we're dealing strictly with a heat transfer situation, this is then going to be Q. Because Q is only involved with the internal energy. The reason I went through that is because now this is something that is solvable. Isn't it? We can integrate that, can't we? All right. Or you can also write it as this. The change in S is also then the change in H over T. All right, so we're out of time. I don't have enough time to do a problem. Do I have a problem prepped? All right, so we will do some problems out of the beginning of chapter 5, then on Thursday.
Dr. Mead.
Yeah.
So is since enthalpy, or sorry. Yeah, always increases. like the delta-
Entropy.
Entropy always increases, is delta S always be positive?
Okay, so the answer to that question is no. Entropy always increases in terms of the universe.
Okay.
Okay, so if I put, if I put my pot of boiling water out on the counter, right? The entropy of the water itself is going to decrease. Right, but the entropy of the air around it ends up increasing.
Exactly, because heat went into.
Because heat went into the air.
Okay.
All right, so when we say entropy is always increasing, we're talking about a universal entropy.
Okay.
Yeah.
So where
Alright.
one decreases one,
Yeah, you gotta
something
go-
else.
Something else has to, it has to always balance out.
Okay.
Vector calc.
We're gonna use it equaling 0 if it's reversible.
Okay.
So we're gonna figure out, is this system reversible based on whether or not the S equals 0?
Okay.
That's a lot of the problem.
I didn't finish it. I didn't finish it.
Bye-bye. You're welcome. Say hello for attendance, please.
Looked it out, but no.
I was so angry.
How did you guys?
It's all right.
Invisible, I was all, I got so behind and it definitely showed on that. Exactly.
I like following the.
Oh,
I
yeah.
got
We
like
did
a-
good on this.
I got like a 68 over the second. Well, if I do the test right, it's like an 8.
Oh, yeah.
And I got 100 on my first. So average.
Oh, that's good. Yeah, I know, I'm still, I'm like, hopefully the final exam is, or also the written papers.
Okay.
That shit's.
Yeah, we'll put it in the pile that got already started.
Oh,
Don't put it in the statics pile.
I know.
Okay.
You told me to come to you.
I just finished it.
Oh.
I took attendance. I want to make sure I got you.
Very well. So I had a question a long time ago. Remember the career fair event where you said it was extra credit?
Yeah,
Would it be possible for me to share like, cause I went, like the image with you and right, like what I,
yeah, send me an email. Yeah, there was a thing to upload it.
yeah, I totally missed that. I'm sorry.
That's okay.
Well, thank you.
You're welcome.